Turn over to page 97. You're going to do experiment 4.5. What you're trying to do, you have water in your bowl, you have a square of toilet paper. I would use the smallest one you can get away with because the bigger, did you hear me? Use the smallest piece of toilet paper you can get away with, not paper towel. That is paper towel, Zach. Do not use that. There's toilet paper back there on that back table. Just hang on a second. Smallest piece you can because you want it to sink, and if you get a big piece, it's going to take forever to sink. Yeah, the paper towels to clean up, not to use to do this, all right? So small piece. See, it says here, tear off 1 square of toilet paper, cut a rectangle out of the toilet paper that should be about this big. Okay, that's about the size you want. Set the paper clip, so you're going to float the piece of toilet paper. Listen, listen. Float the piece of toilet paper on the water, and then you're going to float the paper clip on the toilet paper. That's the tricky part. Okay, get it all to float, and then sit back from your table, because if you bounce the table, that dude's going down. Okay, so sit back from the table, and you want to float it, because when you get it, you got water? Okay, when you get it floated, listen to me, when you get it floated, don't bang the table, call me, and I'm going to come over, and I'm going to put a drop of soap in it, and you're going to see what happens. I'll be right back. I'm going to get that other
2 inches by 2 inches.
Okay. Now,
Set the paper clip on top of the rectangle of toilet paper in the middle. Oh, dang it. I don't have scissors anymore.
Yeah, is it big enough? Try putting the paper clip on.
I don't know.
don't use paper towel. Use toilet paper. It's too thick. It won't work.
We'll both try. Rip it in half.
How's this?
That's pretty good. That is good. But I think it needs to be a square 2 by 2.
Try putting the paper clip on. Just the paper clip.
Is this okay? Is that okay?
Does the paper clip fit?
Yes. How's this? Like, is this?
That's too big.
This is 2 inches by 2 inches. It's about 2 inches long. Should this be okay? Right? No, wait. It's wait. It says it has to be 2 inches long and 2 inches wide. That's 2 inches. We'll try both.
Don't put it on. She said she'll cut it out. There we go. Yeah, don't touch the table.
It really is like bending.
Don't touch the table.
Wait, she said don't touch the table. Okay. Yeah, you can see the water goes down.
But the reflection of the light. The paper towel isn't going
wait, no, maybe we're supposed to like maybe it's supposed to say because that's how we get done. Right, it's dying. It's experimental error. All right, guys, you need to look up here real quickly.
We have the paper clip on the.
Oh, excellent. I'll be there in a sec. I got to do this before it melts. I have a cup of water back there. Would you please, a glass of water, please? No, this is butter. So that's why I've got to do it quickly.
Oh my God.
Here we go. I'm going to try to just do a drop, but this is going to be tough. Okay, you got to see. Can you see? There it goes. Okay. We saw it. So. Oh, excellent. I'll be there in a sec. I got to do this before it melts. I have a cup of water back there. Would you please, a glass of water, please? No, this is butter. So that's why I've got to do it quickly. Because it will firm back up. Thank you. All right, shh. Listen up. Look up here. Guys, Got to watch this now because it's not going to last long. Got a piece of butter here that's not melted. Got melted butter here. Straight to the bottom. Did everybody see that? What about ice? Stays on the top. That's what you were supposed to see there, okay? Because this is odd. Water is odd. When it freezes, most substances, when they freeze, they actually get smaller. They take up less space. So the molecules actually get closer together. Remember, they were dancing, and then they go, So they take up less space, not water. Water is busy holding hands, line dancing, and because of the hydrogen bonds, so when it freezes, they actually have to shake loose each other's hands, and they move apart. The molecules move apart. And because they move apart, water in the frozen form actually takes up more space than does liquid water, and that's why it floats. Now that's very important. We're going to come back to that in a second. Okay, guys, let's go back to the first one first. Okay, the first experiment, what we were supposed to see there is that, like I said, ice floats. And the reason ice floats is because the water molecules release the hydrogen bonds between them for it to turn into a solid. And therefore they spread out. Have you ever made the mistake of freezing a liquid drink that's water-based like milk or something else and it broke the glass or it broke the bottle? Oh. Yes, you've done this.
Like literally yesterday.
Okay, so Carter knows. And Mom gets all excited. I know, I do. And so what you did, tell Mom it was an experiment, but you still need to clean it up. What you did was you actually saw that when water turns to ice, it spreads out. And that's why it'll break the glass, because it is actually in the process of spreading out, okay? And that's why it did that. Okay, because of that, the same space is no longer taken up for that volume of water. It takes up more space, and therefore it's less dense than liquid water. And that's why it floats on top of the liquid water. Now that is absolutely important to life on planet Earth. If it didn't float when it freezes, then every winter the water would freeze from the bottom of the lakes up and the bottom of the ocean up, and it would kill all life in the lakes and the oceans on the planet, which means all of us would die. So it is absolutely imperative the water floats on the top, because then when it floats on the top, underneath it, the life in the lake or in the ocean can actually stay alive because it insulates the water that's underneath it, and it allows it to stay a solid temperature, which is right around 4 degrees Celsius. That's why the fish and stuff. Yep, it won't, the entire thing won't freeze, just the top will freeze. And it's because water floats when it freezes, and that's because of hydrogen bonding. Isn't that cool? So it's really quite cool how water works. And water, actually, what happens, I don't know if you know this, but when water cools, it becomes less dense, and it sinks and it sinks and it sinks until it gets to 4 degrees Celsius, which is about 38 degrees Fahrenheit. It's cold, but it's not frozen. And when it gets to 4 degrees Celsius or 38 degrees Fahrenheit, then when it keeps getting towards freezing, it starts to get less dense again. It comes back to the top and it freezes. Do you know what that does? Not only does that bring that back up to the top so that it freezes, but it circulates the water. Is that cool? I'm telling you, water is cool. You think, oh, it's water. No, water is cool. And the reason water is cool is God has just given it all these really unique properties so that there can be life. And you and I don't even think about all the silly properties that it has, but it's got all these really, really neat properties, and we can do experiments with it. So that next part was, let's answer the questions on page 97 first. On page 97, 410, it says water has a very high boiling point, which is the temperature where it goes into the gas phase, compared to most other substances that are liquid at room temperature. Why is that true? And he wants us to use that hydrogen bonding to explain it. Do you want to tell me?
It takes a lot of boiling to get the hydrogen bonding to come apart.
Very good. It takes a lot of energy to break those hydrogen bonds, or in other words, Ben's got to hit them really hard to break those hands, right? So that they can start flying into different directions. Ben, don't go home and do this because I said that though. All right. And then on page 97, 411, Butane is a gas at room temperature, but it is stored under pressure as a liquid in a butane lighter. The chemical formula is C4H10. Did I read that right? I don't have my glasses on. Did I get it? Thanks. Isopropyl alcohol, commonly called rubbing alcohol, is another liquid you might have around the house. Its chemical formula is C3H8O. One of these liquids participates in hydrogen bonding. Which one? The one that's liquid at room temperature. The reason it's liquid at room temperature, see, you thought it was some chemical something. It's not. The reason it's liquid at room temperature is because of the hydrogen bonding. Otherwise, it would be a gas. Okay? Nobody answered. Did nobody get that answer? No? Okay, do you see what he's looking for? Just if it's liquid at room temperature and it's one of these kind of questions, it's okay. In the last test, if you didn't know what the answer was, you should have written polar vortex, right? On this test, if you don't know what else to answer, put down hydrogen bonding. Okay? Seriously. All right, and then we get to cohesion. And cohesion, it defines for us as the phenomenon that occurs when individual molecules are so strongly attracted to each other that they tend to stay together even when exposed to tension. So in other words, cohesion is when things hold together even when they're pressed. Okay, they hold together even when they're pressed. And you just did this experiment where, and actually, okay, we'll do it together. You just did this experiment where you actually floated that water actually beads up, okay? They are attracted to one another, these water molecules, and so they hold together even when there's tension against them, and that's why water beads up, and that's why you can draw water. Have any of you ever siphoned water in a straw? You've done this. I know you've done this. And then you took it and you put your finger over it and you did it on your brother's plate or something, and your mom got upset? Yeah, okay, I know you've done this. All right. Well, that's got to do with cohesion, that you can actually pull it up and hold it in there and do weird things like that, is because those molecules hold together. And so it's described as cohesion causes surface tension, and so that's kind of the skin over the water that the paperclip was able to float on. And we're told that certain, remember the hydrogen bonds kind of make that skin on the water that allows it to hold things, and that's why we see that it will actually bead up. And that's why certain critters can run across the surface of the water, kind of on the skin of the water, because of surface tension due to the cohesion. And then it mentioned here that that's actually what pulls the water up in plants, we think. In biology, remember, plants, trees don't have a heart to pump the blood up from the roots, the water up from the roots to the top of the tree. We have a heart to pump our blood, right? Plants don't have that. Well, we think that when the water gets pulled out of the leaves, it literally, like a straw, sucks the water up from the roots, and that's how it gets pulled up to the top of the tree. We're not sure, but that's what we think. It's called the cohesion tension theory. Cohesion tension, it says here, cohesion tension transport, but in biology it's called the cohesion transport tension theory. Okay, and that's how they think that it moves from the one place to the other, but they're not absolutely sure. Okay, and so there's one more experiment. It says on page 100, it says to rub half of the glass surface with candle or wax. So I'm going to go like this. And I have enough of these for everybody, but you'll be here for the rest of your life if we do all of this. So I'm just going to show you. Thank you. And so I've rubbed half of the cup with wax. Does everybody see it? Okay. Thank you very much. Yeah. Oh, that's fine. That's just peachy. That's just fine. So everybody, can you guys see it? Yeah. Can you see it? Yes? That's a very 50s term. Okay. And then it says to hold the glass surface horizontally, put it under the sink, and turn the tap on so the water flows over the entire glass surface. Turn the water off while it's still horizontal. Notice the difference between the two sides. Okay, so I'm going to pour. This is our tap, okay? So I'm going to go like that, so it's going over both halves. Wow, it's warm. Okay. What do you notice between that one compared to that one? There's the waxed half, the unwaxed half. So on the waxed half, it was beating up. On the unwaxed half, it just washed right off, right? And we're told here that that is because the unwaxed portion, the water was attracted to the glass. But in the waxed portion, the water wasn't attracted to the wax, and therefore it attracted to the other water molecules, and so it beaded up like little dots. Now, we want that on our car, don't we? We wax our car so that happens. We put, stuff on our windshield so that happens, so that the water will get off of those areas. We want spot-free rinse in our dishwashers. We do all that kind of stuff, don't we? So the water washes away. But that experiment was to show you how the water clumps up. And that was what we had pictured here, was how the water clumps up. Some plants, have kind of a waxy surface on their leaves. And so that means that the water is more attracted to the other water molecules, and that's when it beads up rather than being attracted to the leaf. And if it was on the glass, the part that wasn't waxed, the water was more attracted to the glass, so it just spread out over the glass. Does that make sense to everybody? Okay. And then we get to hard water and soft water, which is really fun because here in Florida we have very hard water. Hard water is caused by the ground that the water goes through. And this just shows you if you have soft water, which soft water doesn't have the particles of rock, and the rock particularly it mentioned was calcium and magnesium, I'm pretty sure. Let's see, yep, calcium and magnesium. But those are both metals, and those are found in rocks. And our water goes through the ground, and therefore it goes through the rocks in the ground, and it picks up little pieces of rock, metals and rocks in the grounds, minerals. And so as it runs through the pipe, it deposits those minerals, and that's why it's called hard water. Soft water doesn't have those minerals in it, and so it doesn't do that. And I brought you, this literally came out of our hot water heater. And I want you to see, it's like rock. It's like pieces of rock. And I only kept some. And when my husband found this all on the bottom of the hot water heater, he was able to save it and we didn't have to replace it. But it's because we have very hard water. Now, I live in the country, and that's why we had this. You guys live in the city, so your water's not as hard. But water in Florida is hard. And have you ever noticed soap scum in your bathroom? That's hard water. That's what hard water does. Hard water will also stain things. And so it's best to remove it is to actually use a chemical reaction to remove it. That's why your mom goes and buys Lime Away or something like that, because it will actually chemically remove that. It makes a chemical reaction and actually chemically removes that. Sorry. And it'll chemically remove it. Yes?
Is like the hard water, why like the well water smells so weird?
Some well water smells weird because there's a high content of sulfur in it, and sulfur stinks. Yes, and so you're smelling some of the gases that are coming out of it. Yes, sir. And here in southeast Florida, there is a large amount of sulfur in the well water, and it also, have you noticed that where people have well water to sprinkle their lawn, sidewalks turn orange or brown? Yeah. That's an iron. That's the iron content.
North Carolina too. Like my family has a house there, and like we have well water, and it smells really weird.
That's interesting because up there they have pretty soft water because the rocks that it's going through are different. But you're smelling gases in the water. Yeah, that's what you're smelling is gases that are actually dissolved in the water. In North Carolina, notice the difference when you wash with hard water or when you wash with soft water. And this is why a lot of people go ahead and put a water softener on their house so that they don't have this problem. If you work in industrial cleaning situations where they're washing car washes and stuff like that, they'll have a water softener because this helps it to clean better because this is a hard situation for people to deal with. And so the water is either hard or soft because of the rocks that it moves through. It's not because of something that is done to the water. It's actually because of the water passing through certain rocks and whether it picks up those minerals or not. Okay? So I want you to understand that, and we do soften water. I remember in North Carolina was where I first noticed that soft water the soap acts like it's possessed. I was taking a shower at a friend's house in North Carolina, and I put the normal amount of soap on my body, and I took my shower, and I couldn't rinse it off. It wouldn't leave. And I'm like, what's wrong with the soap? Well, there's nothing wrong with the soap. What's wrong is that I'm from Florida. I'm used to hard water. Hard water, the soap, you use more soap. Because of our hard water, you end up using more soap, and it's real easy to wash off. Whereas with soft water, man, the soap just suds like it's got its own mind. Yeah, you've noticed it. I can see Carter's face. He's going, yeah, okay, possessed soap. Ah! Anyway, all right. So this last question on here, it says on page 101, it says calcium and magnesium are both the results of atoms that lose electrons. Thus, they are positively charged ions. Suppose you actually could remove calcium and magnesium ions from water without replacing them. You know what? This is just a really hard question, and there's nothing like it on the test. We're going to skip it. Because every time I read that, I think, why did he ask that question? It was like he had a hard time coming up with something. So how do you get hard water? Is it something that's added to the water? How does hard water happen? Tell me. Why is the water soft in North Carolina and hard here?
Rocks.
Thank you. High five. Nick's got it. All right. The rocks that the water passes through. Remember that, okay? The water's either hard or soft because of the rocks that the water passes through. And water's always passing through rocks, isn't it? Because when it hits the ground, then it passes through a bunch of stuff. So, okay. And that's a good thing because it picks up minerals and stuff that God meant for us to get in our water. Thus, we drink mineral water. Oh, okay. On page 104. You there? Study guide 104? I love the picture on 105. Don't you love that picture? It's a great picture. It's the picture of the Earth from space. I like that. So, we're going to go around the room and we're going to try this and see how it works, okay? So, Rachel, would you tell us what electrolysis is, please? Did you happen to do that? Did you do your study guide?
Yeah.
Do you have it?
Yeah.
I'll tell you what, while she's getting that out, Amanda answered you read the last thing, right? So, Colin, do you have your study guide out?
I got it.
Oh, Rachel's ready. Get your study guides out. If you don't have them out, get them out. Okay, Rachel.
You said the electricity to break a molecule down into smaller units.
Very good. So it's when we use electricity to break apart a molecule. What's a polar molecule?
It's a molecule that has a small negative charge and a small
Very good. It's got a slight charge over it. Do you remember why? What's happening to the electrons? Are they shared evenly or unevenly?
uneven.
Good. There's unequal sharing of the electrons, and that's why. Very good. Thank you. Okay. So Lydia's going to tell us what a solvent is, please.
It dissolves things.
Good. High five. I like it. It's short, too. Dissolves things. All right. How about the solute, Caleb?
A substance that is dissolved in the solvent.
Very good. So it's being dissolved. Excellent. How about cohesion, George?
Cohesion is like how the molecules stick together.
Good. It's when they hold together. They're attracted to each other. Very good. That was a hard one, I know. Okay. And then hard water. Nick, boy, it seems like you just keep answering that question. Go ahead.
Water goes through a lot of rocks.
Good. And so it's got particles in it. Very good. Thank you. And guys, if they ask, remember it's calcium and magnesium, but the point is it's got minerals in it. Okay, thank you. So then number 2, suppose you did an electrolysis experiment like 4.1 on hydrogen peroxide, which is H2O2. God bless you. If it worked properly, which of the following results would you expect? A, same as with water. B, equal amounts of hydrogen and oxygen. And C, twice as much oxygen as hydrogen. And so, do you want to help me with that, Sarah, or you want me to do it?
Is it B?
Very good, it's B. Remember, regular water would be this. That was very good, Sarah. But this is hydrogen peroxide, so you would expect them to be even if your experiment actually worked correctly. Wow. Very good. Thank you. And then on the next one, it says, suppose you perform 4.1 with a crack in your test tube. Gas could slowly leak out of that crack, but not nearly as quickly as it's being made in the experiment. Suppose further that the crack was in the test tube that held the hydrogen. And so what we have is we have this scenario, but we have a crack in this tube. So what's going to happen to our gas level? It's going to go up, isn't it? Because it's going to be leaving, so it might look more like this. So then in that case, which answer would you expect to have? Would you expect to have HO or H4O? HO. And I would actually draw that to see it personally. I would, so make sure I could answer. Very good, thank you. Emma, Epson Salts, which you used in experiment 4.1, has the chemical formula of MgSO4. If Mg is magnesium, S is sulfur, O is oxygen, how many of each of these atoms exists in this molecule? So how many magnesiums?
1.
How many sulfurs?
1.
How many oxygens?
4.
Good job. Okay. Number 5, calcium carbonate is an ionic substance commonly called chalk. In this molecule, you have 1 calcium, 1 carbon, and 3 oxygens. What is its chemical formula?
CaCO3.
Excellent. Thank you, sir. The other Zach, one of the most common household cleaners is ammonia, which has a chemical formula of NH3. How many atoms are in the molecule of ammonia?
3.
Let's do this. NH3. You have 3 of these, but Zach, how many of those do you have?
1.
So how many total? 4. Make sure that you don't forget to count the invisible 1. That'll come back to get you on a test, okay? So make sure. Good job. Thank you, sir. Let's see. Number 7, Cal. A certain molecule is composed of atoms that all pull on electrons with the same strength. Will this molecule be polar? No, because remember, polar molecule, unequal sharing, right? Very good. Okay, number 8, baking soda dissolves in water. Will it dissolve in vegetable oil, which is a nonpolar substance? It's your turn. No, very good, it won't. Thank you, Wyatt. So we're back to clay. Clay, carbon tetrachloride will not dissolve in water. Is it most likely made of ionic, polar molecules, or nonpolar molecules?
Non-polar molecule.
Very good. Thank you, Clay. Carter, suppose you were about to count the molecules in a substance. Which would have more molecules? 1 liter of liquid water, oh, this is a tricky one, or 1 liter of ice? What did you put for?
1 liter of water.
Very good. The liquid water. Remember, the liquid water, they're more tightly packed, and the ice, they spread out. So in the liter, you would actually have less molecules in the ice because they spread out, so you'd lose some than you would in the liquid water. That's a tricky question, though, in my opinion. How many of you thought it was a tricky question? Am I the only one that thought it was tricky? Okay, thank you. I appreciate that. All right. Ben, if the substance in question 10 were virtually any other substance, what would the answer be? Would it be the solid or the liquid?
Solid.
The solid, like we saw with the butter. Right to the bottom, right? Thank you. And then, Colin, number 12. What is responsible for water being a liquid at room temperature as well as for water's cohesion? What was the answer you'd give anytime you weren't sure what the answer was in this chapter? Somebody help him.
Hydrogen bonding.
There you go. Remember that? Hydrogen bonding. If you can't answer anything else, write hydrogen bonding. It will get you through a lot of things on this test. Okay, Colin? All right. Thank you, ladies and gentlemen, for helping. Number 13, what causes surface tension? Which is caused by?
Hydrogen bonding.
Hydrogen bonding. That's right, but it is cohesion, but it's caused by hydrogen bonding. That's why I said write it down if you can't think of anything else. Okay, number 14, why is water harder in certain regions of the world than in others? Why? And I guess whoever wants this one, because we've been through everybody. Does anybody want this one? You want me to do it? Because... Did somebody say it? Because of the rocks that the water moves through. It just depends on the rocks that the water moves through and what they're made of as to what you're going to get. Now, you're not allowed to leave. We have to clean up now. Remember, you're going to take this test and read the first half of the next chapter.